Hello, and welcome to my series covering the Ultra-Scale Playbook part by part. In each video, I cover one section of the Ultra-Scale Playbook, and it's followed by a Google Colab exercise, which I heavily recommend that you complete because while knowing the theory of the paper is very essential, applying it is just as important, and I hope you enjoy the video. Okay, so here we have a full training step with each rectangle representing one layer of the model, and here we have the model itself. So if you can think of a transformer, for example, each one would be a transformer block, and we feed in at the very beginning our tokenized and positionally encoded sentence through the transformer block, and then at the very end there will be a softmax over the vocabulary to calculate each subsequent token. So this top is just simply the model, and then we have, well, our forward pass, which flows through the model. So in this case, input data is passed through the model to compute predictions, and activations, which are intermediate outputs, are stored for the backward pass. And we use the activations in order to calculate our gradients, okay? So, and the gradients, of course, occur in the backward pass because we need to do a full forward pass in order to compute our loss. And then once we have our loss, we can compute, we can backpropagate through to calculate our gradients with respect to the loss. And gradients indicate how much each parameter should change to minimize our loss. So we have our gradients, but then when we update our model, it's not efficient to just use the gradients directly. Instead, we use an optimizer, which will use the gradients in the most efficient manner, ideally, to modify our parameters. So the gradients are used to update the model's parameters using the Atom optimizer. So to give a resume, our model computes a forward pass. And if we think that we have a transformer, then we usually take the cross entropy between the target token, whatever token is actually in the training set, and the softmax distribution of what our model computed. And then we use this to calculate gradients with backpropagation. And then we use the gradients and an optimizer to update our model. So now let's look at the memory profile of the first four training steps of Llama 1 billion. So you can see this graph. I'll quickly move my camera for the full picture, but in this bottom left corner, there's not that much important information. And every single color corresponds to one category of memory. So the major ones would be activation, so the intermediate outputs that are stored during the forward pass. There's also the gradients, which is this orange color here. We have our parameters themselves, which are constant because the parameters of the transformer model are fixed. They do not change over time. The optimizer state is here. And then what do we have? Otherwise, unknown, autograd. So those ones are not as important. One thing that I'll quickly point out to begin is that the optimizer state does not exist for the first iteration. So this would be this training step here. And this is because since optimizer takes momentum, it requires multiple training steps to have occurred to perform this calculation, or else in some implementations you'd be dividing by 0. So our optimizer only exists after the second iteration. And first of all, you notice that whereas each forward pass leads to a spike in activation in the second, third, and fourth, which makes sense. So when we do a full forward pass, right before we start backpropagation, the activations that are stored are at their max, and they slowly decrease. Why is that the case? This is because during backpropagation, once we use our activations to calculate the gradients, we can then discard our activations up to that layer such that over time, for example, if we reach this layer here, we will have discarded the activations up to that point starting from the end of the model. So this is why, once again, our activations decrease while the gradients increase over time. Unknown can just be attributed to CUDA or other background processes. It's not very important to kind of know what's going on there. And then one thing that I would like to point out is why does the activation spike up here, just like in the other cases, up to around 50 gigabytes for the 1 billion parameter model, and then plateau in the first iteration. And this is because PyTorch uses a caching allocator that does prep work in the first training step to prepare memory allocations for the subsequent steps, so it does not have to search for free memory blocks. So this is just essentially memory allocation. This is why it's lasting for almost, I don't know, like half a second instead of the very infinitesimal amount of time for the peak of memory at the training run. But what is worth noting is that you can see this dotted line here. Even though we use around 60 gigabytes of memory for a very small amount of time throughout the entire training run, you still need this amount of memory to complete the training run, or else you'll have a memory overload during the run. Now let's look at the memory used for each parameter with respect to the parameter count. So starting with the parameters themselves, these are the weights of the attention layer, the feed forward layer, layer norm, etc. And the size depends on precision. So in this case, we're assuming that we have a float 16 or BF float 16 format. So we are multiplying by 2 times the number of parameters because it's 2 bytes. And same goes for our gradients. Gradients have the same size as the model weights and are stored during the backward pass for the parameter updates. Once again, now if we skip quickly to the optimizer states, Atom stores additional information. So this is going to be momentum and variance. Therefore, it requires 8 bytes per parameter, 4 bytes for momentum and 4 bytes for variance. And this is because for training stability, the parameters would also be stored in float 32. And once again, this is for the optimizer step. However, this is not standard per se. Every practitioner will train their model in their own method, but in this case, our parameters and gradients would be stored in a 2-byte format, whereas we would still keep the parameters in a 32-bit format as well, 4 bytes, in order to use that for our optimization step when we update our gradients. So the last feature of the video will be looking at how we can compute the parameters of the transformer architecture overall. So let's first look at this image of the decoder transformer and compare it to the formula that we have here. So the total number of parameters would be equal to the embedding layers, which would be these 2 blue keywords here, plus the transformer layers, this entire transformer block, and other. So I'll explain every part individually. Let's start with the embedding layers. So we have a word token embedding, which is this statement here, and a word positional embedding. And that's this line here. So the positional embedding gives each token in the sequence its position, since multi-head attention as an operation does not depend on the order, and therefore we need to embed the order before we give it to the transformer block. And then we also have our word embedding, which will convert our tokens to their transformer embedding dimension. Okay, and now in our transformer block, these LN1 and LN2 stands for layer norm. So in this case, we have a pre-layer norm. However, in this specific model, which I just got on the internet, it's using post-layer norm, which is to say that we add the norm after as opposed to before the attention and feed forward network. However, since addition is commutative, in terms of just the parameter count, this does not make a difference whatsoever. And then of course, attention is here, multi-layer perceptron is here, and then why is there a final layer norm? And it's just because this is the formula for GPT-2. And in GPT-2, in fact, there is a layer norm at the end of the last transform block, which if we have 12 layers in GPT-2 would mean we have a 13th final function, which is the layer norm, before we multiply the last transform block output by the vector, which is vocabulary length by embedding dimension, so that we can take a softmax. Okay. And now if we go down, we will expand these formulas. So in the case of our word token embedding, it is the vocabulary size multiplied by the embedding dimension. And for our word position embedding, it's just the number of positions multiplied by, once again, the embedding dimension. Okay. We're going to skip the attention because it's more complicated and just focus on the other 3 computations within the transform block. So we have our layer norm. And for the layer norm, it's 2 by the embedding dimension. So this is, for example, in GPT-2, 768. Why is it 2? And this is because for every single value in the for every single embedding element, we have a mean and a bias term that we add to it in order to normalize. So for every 768 terms, we have a scaling factor and in addition, the bias. So this is done once and twice in the transformer block. And then we have our multi-layer perceptron. So it's 2EH plus E plus H. Why is this the case? So here's a table with all of the different values, which I'm referring to in this calculation. So E, once again, is the embedding vector, and then H is the size of the hidden layer within each transformer layer. So usually this is 4 times the embedding layer. So since we have both an up projection and a down projection, we have EH twice. And then in addition, we add a bias term to each of the projections. So for the up projection, we will do plus H because the temporary dimension of our residual stream will be 3072. And then once we down project, we will also add E, which is just the normal residual stream dimension of our transformer. So there you go for the formula of our MLP layer. And then this final linear layer, layer norm, not linear layer, is the same as the others. So 2E. Just ignore this accumulation of the values because I think that this loses information since you're just combining everything. Of course, if you just want to compute the parameter count, then this is useful, but I like it when it's in the expanded form. And then finally, if we just move this slightly down, I have the attention score calculation, which I'll also go through one at a time. First of all, we have E times 3E. Okay, so what is this? So we have our embedding dimension squared times 3. So the 3, you can intuit, comes from the fact that we have a query, key, and value matrix in our attention calculation. And those are each E by E. So 768 by 768. In the case of GPT-2, there were 12 heads for the multi-head attention, which means that each head dimension was 64 in length, so 768 divided by 12. But in any case, the full query, key, and value matrix were all 768 by 768, and there was 3 of them. So E squared times 3, and then each one also has a bias term for each element within the matrix. So instead of E squared, now it's just 3 times E, or 768 times 3, because each embedding dimension has its bias term. And then we add E times E plus E. And this is the output matrix, which after our scaled dot product attention, so we have our QKT divided by the square root of the head dimension, and then we take the softmax of that and multiply it by the value matrix. After this, then we will multiply it by another 768 by 768 matrix to combine the heads for the subsequent MLP step. And this is a 768 by 768 plus 768 bias matrix. That's everything for part 1 of the Ultra-Scale Playbook series. Tune in for part 2.